Yeah.
So we have this ARM TDMI core, which is the main processor for us, and all the like if you see, these are buses. Okay? So if you see from ARM TDMI core to all other peripherals, like these are peripherals, external interrupt, capture or timer, analog to digital converter, digital to analog converter, general purpose IO, pulse width modulation. These are all the features what we discussed yesterday. So these components, you have to just remember the feature and just draw the components for them. And like RAM, ROM, flash, right? This is the overall architecture of your LPC2148. Okay, and very important thing here is the bus architecture. Okay, internal bus. So here in ARM processor, right? Like you can see some bus which is flowing, right? The data which is flowing. So this data flowing through a bus, special bus in ARM called AMBA bus. AMBA bus. So AMBA stands for Advanced Microcontroller, Advanced Microcontroller Bus Architecture. Okay, Advanced Microcontroller Bus Architecture. This is like if you consider any microcontroller or microprocessor which is based on ARM architecture, that bus will be AMBA bus. AMBA bus. So basically, based on the speed of this AMBA bus, right, it is further divided into various buses. Like one is local bus, which is actually the fastest bus. So you can see here in this architecture, you can see like some of the buses which are connected to memories, right? Like you see like internal flash, internal RAM, and fast general purpose IO. So this particular bus is corresponds to the local bus, okay, which is the fastest bus. So you can see here this bus, right? This bus is the local bus, and we have AHB, that is Advanced High Performance Bus, AHB bus. In order to connect to this ASP bus, right, it basically we interface to various different peripherals. You can see in order to connect to this AHB bus, that is Advanced Peripheral Bus, we use something called AHB bridge. Okay, so the AMBA bus basically it uses the AHB bridge, which can communicate to the multiple peripherals. Okay, multiple peripherals. It's like acts like a uh, communication point. The AHB bridge acts like a communication point where it can connect to the multiple peripherals. Okay.
Yes, sir.
We have another bus, that is VPB. That is a slower bus, VPB bus. VPB bus. That is slower speed bus. Which actually like communicates with like other peripherals which are like not high speed application. Okay, I mean, see, more the speed it consumes more power. And in many case, like we don't want any faster data transit, right? So, for example, you have like 1 byte of data which is getting every second. Then there is there is of no use if you have 1 gigabits per second bus. Very low speed bus also is sufficient. For that application, we use VPB bus. So usually in VPB bus, right, we will have like a clock divider, which divides your processor clock, whatever the processor clock you have, right? So that clock it will generate another clock that is called P clock, which is like 1/4 of your processor clock, C clock. So C clock is the processor clock, okay, and P clock is the peripheral clock. Peripheral in the sense all this SPI, UART, these are the peripherals. So P clock will be 1/4 of C clock. If my uh, processor, that is processor is this ARM PTMI, if it is running at 100 megahertz, then this P clock will be running at 25 megahertz. Clear?
Yes, sir.
Next, we have like various memories connected, interrupts connected. So how this memory map is arranged, right? So that we will look at. So if you see here, the total memory space of LPC2148 is, like how many bits it is? It is having 32 bits, right? 32 bits LPC2148. So we can have 2 power 32 memory space that corresponds to 4 GB memory. So LPC is capable of addressing 4 GB memories. Okay.
Yes, sir.
So if you see the architecture wise, so I mentioned like the LPC2148 has 512 kilobits of volatile memory, flash memory, right? So like from 0th address to 512 KB, it is dedicated to flash memory. Okay. And from 1 GB address, 1 gigabit address, we have 32 kilobits SRAM address. So here, right, here you can map to any peripherals. Like if you want to map into UART or if you want to map into GPIO, this is your wish. Okay. I mean, any data or registers you can map here or like external memory. But here from 3.5 GB onwards, right, they have dedicated mapping like UART or like SPI. They have dedicated mapping for like 3.5 GB onwards APB peripherals. From 3.75 GB onwards, they have AHP peripheral mapping. Okay.
Yes, sir.
This is a general mapping. I mean, as when we discussed about programs, we can go through in detail. Next, how we can generate the CPU clock, that is C clock. How to generate the clock? We have two types of clock. One is C clock, CC clock. Okay, that is processor clock. Another is peripheral clock. So C clock is basically used for running the processor. P clock used for running the peripherals. So the P clock, right, is derived from C clock. So this is the derived version of C clock. So now which is faster? C clock is faster or P clock is faster?
So P clock.
C clock is faster because C clock I am deriving from the P clock. P clock I am deriving from the C clock.
Okay, sir. So what's the difference in between the C clock and the P clock? Like it's just the how it's derived, or is there any other
No,
work
it is
in that?
actually speed wise also. See, this is C clock is only used for your processor operations like adder, subtractor, multiplier, all these cores will be there, right? Internally. For that it is used. We call it the processor clock. P clock used by other peripherals. Which peripherals are there, right? Timer, UART, SPI, I2C, USB, all these things are there, right? So for that we use this. So all the other interfaces, right? We call it as peripheral. That's why it is a peripheral clock. Okay.
Yeah, sir.
In LPC2148, we have two PLLs. PLL. PLL in the sense phase locked loop. Phase locked loop. We generate clock basically. Okay. with the base, somewhere it has to generate the clock. Have you in your basic electronics you might have studied about oscillators and all, right? Generates a clock. So the same way here PLL is basically used to generate the clock. Okay, and PLL0 used for C clock, and PLL1 used for P clock. Okay. Also PLL it actually P clock. Sorry, P clock is generated from C clock, but PLL1 used for your USB clock. Okay, USB clock used for USB clock, which is of 48 megahertz. 48 megahertz. So, but actually PLL alone, it's actually just generates the clock. But in the sense, it has to have some base frequency. Somewhere you should, if it gets some square wave, right, it will convert into the required clock. So the base clock is generated from F oscillator. So usually these oscillators, right, some piezoelectric oscillator will be there. It can be internal to the microcontroller or external to the microcontroller. Okay, so this is basically generated from F oscillator. That is external. So usually your LPC2148 will have two pins, extal1 and extal2. So these crystals connected, and from this is actually generates F oscillator. From here internally we will have PLL in the LPC2148. That PLL will generate overall clock. Okay, and this the frequency of this extal, right, that is crystal, is 12 megahertz. Okay.
Yes, sir.
So this whatever the 12 megahertz is there, so by default this PLLs will generate into 60 megahertz. It will convert from 12 megahertz to 60 megahertz by default. I mean, again you can program. Okay, so generally you can program from 10 mega to 60 megahertz. That programmable option is also available.
Got it, sir.
So if again we know that like from how we derive the P clock from the C clock, right? The input to the P clock generator is basically you are like whatever the C clock is there, 60 megahertz. So 60 megahertz, like that too, like it can be 10 mega to 60 megahertz. So in the P clock, right, we will have something like VPB divider, which generates the P clock. Okay, that is like low speed
So, what is a
peripheral.
VPB divider?
It is
Full
actually
form?
used. It is we discussed, right. It's a VLSI peripheral bus, VPB, VLSI peripheral bus. So that is
Okay, okay, yes,
actually
sir.
for dividing the lower clock, actually, I mean, for the peripheral clock. Okay, so this VPB bus, like by default, it will be 0x00. Okay, in the sense, whatever the input clock is there, it will make it divide into 15 megahertz. P clock will make it into 15 megahertz. But whenever you program certain values to this VPP divider, so this clock can be changed by default, but default value is 15 megahertz. Okay.
Yes, sir.
So as I mentioned, like if you want to interface to any external uh, pins, right? I mean external devices like LEDs or LCD, any IO. So we have to use GPIOs. GPIO LPC2148. So we have actually uh, two ports, and each of 32 bits. Okay. So in port 0, ports means pins actually. Okay, ports is actually pins. So port 0, even though it is 32 bits, okay, we can use 28 pins in port 0. Okay.
Yes, sir.
28 pin for digital IO, that is ones or zero, digital IO, and P0.31 used only for analog signal. Yesterday we discussed, right, what is analog signal? Like speech signal, continuous signal. Okay. And 24, 26 and 27th pin are reserved. It is not available for use. And same way, port 1 is also 32 bit. So out of that, only 16 to 31 are available for use. Okay. In port 0, how many pins are available for use?
So 28.
28 plus 1, right? 29.
Yes, sir.
One I said like for analog, right? 28 plus 1. 3 pins are not available. So 29. 28, correct. Right. 28. 3 pins are not available. 28. Correct.
Okay.
29. 3 pins are not available. 29. So here port 1, 16 pins are available. 16 plus 29. Total in LPC2148, 45 pins are available for use. Okay.
Yes, sir.
So this pins, right, whatever the GPIO pins we saw, it can be configured to multiple application. To what application we have to configure, that is based on pin connect block. Pin connect block. This helps us to decide for what application we are using. Okay, what application we are using that IO pins. Okay, it is like a multiplexer. So each pins, that 45 pins I said, right, in that each pin can have maximum of 4 different functions. 4 different functions. Okay. So in the sense like 45 into 4 different combination of function also we can have.
Yes, sir.
So if I consider any one pin, specific pin, like pin 1, then this pin 1, what function it should perform, that is based on pin select lines. Pin select line. Okay, pin select line. That is 3 bits. 3 bits. Sorry, it's not. It basically not 3 bits, 3 registers. Okay, pin select line, 3 registers. So these 3 registers, like again, it is like pin select 0, 1, and 2. Okay. So in this, if pin select 0 is used to configure pins P0 to P15. Pin select 1 used to configure P16 to P31. Pin select 2 is used for configuring P1.16 to P1.30. Okay, that way like we splitted that into 3 different functionalities. Okay.
Yes, sir.
So usually the 11 and 10th bit used to control the operations. If this pin select, like for example 11th and 10th we use for controlling the P0.5. Okay, so in that, if it is 00, it corresponds to GPIO. If it is 01, it corresponds to SPI operations. If 10, it will be used for timer operations. If it is 11, then it will be AD, analog to digital converter. This is just example of P0.5. So how it is splitted, like actually if I consider P select 0, it's 32 bit, right? 32 bit. So I said like it is like P0.0 to P0.16 it is controlling, right? Every 2 bits corresponds to one pin. Okay, every 2 bits corresponds to one pin. Like this 0 and 1 pin bit corresponds to P0.0. 2 and 3 corresponds to P0.1. So on. This way we have to control that particular pin, like for what purpose? Multi-purpose pin. Hope you got it.
Yes, sir.
We can see actually here, if you see the block diagram, right? You can see every pin, it is showing multiple operation. It can use general purpose IO, cap 0.0, max 0.0. This is basically I'm mentioning. So multiple purpose, like each pin can be used for multi-purpose. You can see here 4 different operations are there, right? RXT, PWM, and P. So using pin select, you can say that like which particular operation you have to perform.
Got it,
Okay.
sir.
So now we will start looking into some programs. Okay. So using GPIO,
So we
we'll start.
actually did stepper motor today. We had extra lab and we did stepper motor, LED, and the keyboard experiment.
Okay. Okay. So we will start with the simple LED examples. So these GPIO pins, as I mentioned, GPIO pins, right? So we have to use GPIO pins for connecting LED switches or relay, right? So
Yes, sir.
the registers used for controlling these GPIO pins, one is IO direction, which mentions whether that pin what you are choosing, whether it is output or input. Okay.
Yes, sir.
So if you set this bit as 1, then it is input. If you set a bit of this register as 0, then it will be output. Next is IO set. Okay. So this register used for setting the output of those pins. Okay. Like for example, if you want to blink the LED, then that particular bit you will set it as high so that LED will be switched on. So if you want to clear that, you will use IO CLR. Okay. Then
Yes, sir.
if you want to read this particular pin, then we will use IO pin. So if you read this IO pin, whatever the value, so for example, switch is there. So you have connected switch is pressed, then you want to read what is the status of this, then we will use IO pin. Okay.
Yes.
So for port 0, we use IO direction 0. IO DIR 0 for port 0. So if I say in IO direction 0, 0x 0 0 0 0 FF FF. So which are the pins are input? Which are the, can you tell me?
So this is a first example. Can you guide me with the example? I'll get to know better.
Yeah. So IO direction 0, basically it says, see, I mean, like if the bit is 1, it means input. If the bit is 0, it means output, right? So you can see
Yeah, sir.
each bit corresponds to one pin. So here we have total 32 bits, right? 32 bits. So each pin, like now if I consider this particular uh, character, it is actually in the binary it is 0000, right? Then it means the pin 31, this is corresponds to pin 31. Pin 31 is set as output. 30, 29, 28, so on, it is set as outputs. And the lower bits, right, pin 0, like F means, what is the binary value of F?
So it's 0.
What is the binary value of F? 1, 1, 1,
Oh,
1, correct?
okay. Yeah. Yes, sir.
So it means actually these bits are set to inputs, correct?
Yeah, sir.
Yes,
So
give me
the
a second.
last 4 are set to input and the starting 4 are set to output.
Not last 4, I mean this together, it is actually, this together, it is 16 bits, right? 16 bits.
Output, yes, sir.
This together, it is 16 bits again. So first
Yes, sir.
16 bits are set as input,
Out.
and next
So
16 bits are,
zeros are output, no, sir.
yes, zeros. These 16 bits are set as output, and these 16 bits are set as input.
Yeah. Okay, sir.
Just give me a second, I'm getting a call.
Yes, sir.
Yes. I hope that point understood, right?
Yes, sir. Now I have a clear idea.
Yes. Same way, like this is just for setting the direction, right? If you want to make it high, then if I make like IO set 0 with 0x 0000 ff, so then these 16 pins will be high, it will be set as high logic node. This 16 bit will be set as low. Clear?
Yes, sir.
Okay, so we will quickly see one code. Okay, We consider this code, like first we will include this LPC2148.h. This is the header file which contains all the details. Like in C program, these are all the things are not there, right? IO set 0, IO directional 0. These are all like variable which we need to refer from somewhere. That's where all this LPC21xh library contains. Okay. This library contains. And I'm calling a main function. Here I'm defining x as a variable. And here I'm setting all the pins as output. So sorry, I mean in the previous statement I made one mistake. So if you make it F high, right, it is output. If you make it low, it is input. Okay. So here I am making everything as high. So I am making IO direction as all the pins as outputs. Okay.
Yeah, sir.
And
So, but in the
here,
next line, just the last 4 digits are the outputs.
no. Here, first, this part, what it means is, can you tell me what it means? I'm calling the for loop, but there is no condition. What it results in?
So it helps in looping without condition until
It
and
is
unless we
actually,
get the desired value.
yeah. Here it will be continuously looping. Here no condition, right? That is kind of infinite loop. Okay.
Yes, sir.
Okay. So it is infinite loop, and IO set 0. I'm making last 4 bits as high, right? Last 4, that is P0 to P3. It means I'm making only last 4 bit as high. Okay, last 4 pins, that is P0 to P3. Last bit corresponds to P0.0, and fourth bit corresponds to P0.3. Only those bits I am making it as high. Then I will give some delay. Then I will clear them. Then again I will give some delay, and it will keep repeating. It will make it high, give some delay, make it low, give some delay. So it will be keep repeating. And if I draw this signal, like if I have 4 pins, that is P0.0, P0.1, P0.2, P0.3. If I probe using some CRO, right, we'll see something like this, the waveform, low for more time, high for some time, because it's asymmetric, right? Here 1000 delay, here 2000 delay. It is actually this for loop basically we use for just, we are not doing anything, right? We are just running the for loop. It is actually for delay. I will make that pin high, then I will wait for some time. I will make low, then I will wait for some time. This way it will generate everything. All the 4 pins, right, will generate. So some square wave will be generated in the pins. Did you understand? And when I say square wave, here if you connect some LED, right, some LED, whenever it is high, LED will be on. Whenever it is low, LED will be off. So some kind of
So then
blinking.
at times it follows a pattern.
That actually here, all the 4 LEDs will be on, all the 4 LEDs will be off. No patterns actually here. If you want patterns, you have to generate like this, right? One. So for example, you have to generate another signal like this. Whenever it is high, this should be off. So then you will get like one LED on, another LED will be on, this will be off. So this square wave pattern you have to change. But now if you see, everything you are making it high together and everything you are making it low together. So all the LED will glow in one shot and all the LED will be switched off in another shot. So in that way it will generate. Hope you understood.
Yes, sir.
Okay. So today we will pause for a day. Tomorrow we will continue with some more examples. Tomorrow we'll mostly discuss with all the interfaces and examples. Okay.
Okay, sir.
Okay. Thanks.
Yeah. Thank you, sir.